All right, so in this section, we're going to be taking a look at two functional groups that are really, really similar to each other. And these are the aldehydes and the ketones, right? And again, we had saw briefly these two functional groups at the end of chapter 11. Here we're going to take a much closer look at them. So both the aldehydes and the ketones share something in common, and that is the presence of a group known as the carbonyl group. And this carbonyl group looks like this: a carbon with a double bond to an O, and then we have two single bonds remaining to that carbon, right? So this carbonyl here is common to both the aldehyde and the ketone. As you can imagine, the carbonyl is a polar group because the oxygen is more electronegative than the carbon, right? So there's going to be a dipole going towards the oxygen in that bond. And don't forget also that there's two lone pairs on that oxygen atom. So the carbon in the carbonyl would have a slightly positive charge. The oxygen would have a slightly negative charge. So both the aldehydes and ketones are going to have that carbonyl group in them. What makes them different from each other is what else is attached to the carbonyl. In the aldehyde, okay, the carbonyl is attached to at least one other hydrogen. All right, so for example, there's my carbonyl, and then if that is attached to at least one other hydrogen, that makes it an aldehyde, right? That's the presence here, or that's the functional group of for the aldehyde, C double bond OH. That could be something else, which we'll just represent as an R group, making up the fourth bond to the carbon, right? This is sometimes condensed into RCHO, right? That's a quick way to represent the aldehyde functional group. For a ketone, what we're going to see is that the carbonyl, the C double bond O, is attached directly to two other carbons. In other words, the carbonyl, the C double bond O, is sandwiched between two carbons on either side, and we can represent those carbons as just R groups. All right, and that's the presence, or that's what we look for to identify our ketone functional group. All right, so both of them, the ketone and the aldehyde, will possess the carbonyl, the C double bond O. Right, what makes them different is in a ketone, that carbonyl is surrounded by two carbons. In an aldehyde, the carbonyl has at least one hydrogen attached to the carbon of the carbonyl. All right, so aldehyde group we mentioned can sometimes be written as CHO. That's just a shortcut to represent an aldehyde, and the double bond is understood to be there between the C and the O. In a ketone, the carbonyl is bonded to two alkyl groups, which just means that there are carbons on either side. And sometimes the keto group, the C double bond O, is represented as a CO. All right, so those are just shortcuts for representing the aldehydes and the ketones. So let's take a look at the nomenclature, or the naming of the aldehydes and the ketones. So an aldehyde, we're going to follow the IUPAC naming system first. So the IUPAC name is going to come from the alkane. So we're going to take the alkane name, drop the E, and replace it with AL. All right, so it may not seem like a big deal, but we saw when alcohols were named, the ending was OL. With an aldehyde, the ending is AL. All right, so for example, if I had a 1-carbon aldehyde, which would be this, right? A 1-carbon alkane would be methane. All right, so what we're doing is we're going to drop that E and replace it with Al. So a 1-carbon aldehyde would be methanal. All right, similarly, a 2-carbon aldehyde. Okay, so there's my aldehyde group. Now it's attached to another carbon. Well, we start with the corresponding alkane. A 2-carbon alkane would be ethane. For a 2-carbon aldehyde, we drop the E, replace it with Al, ethanol. All right, so that's the systematic way for naming our aldehydes. Sometimes you'll see some common names being used to represent the aldehydes, and those are pretty obvious when you see them because the common names actually end in aldehyde. Right, so a 1-carbon aldehyde is sometimes called formaldehyde, which is just a common name for methanol. Right, and you probably have heard of formaldehyde before. It's used as a preservative for biological specimens. Similarly, a 2-carbon aldehyde, the common name for it is acetaldehyde. And that's the common name for ethanol. Right, so the common names end in aldehyde. The IUPAC names end in AL. And we're going to preferentially use the IUPAC name because that's the systematic way to name our substances. All right, so we saw methanol, a 1-carbon aldehyde, ethanol, a 2-carbon aldehyde, and we can keep going. Propanol would be 3 carbons, 1, 2, and 3, and then butanol would be 4 carbons, 1, 2, 3, 4. So you'll notice that in all of these cases, the carbon of the carbonyl, okay, must be carbon number 1, right? If you're going to name this thing as an aldehyde. Because what you're saying is when you name it as an aldehyde, that aldehyde group preferentially is going to get priority, right? So that C of the double bond of the carbonyl has to be carbon 1, and you'll notice that because the aldehyde always ends in an H, right, there's nothing that we can attach to that H because hydrogen can only form 1 bond. The carbonyl is always going to be at the end of a compound for an aldehyde, right? There's nothing else attached on this side in any of these, right? So the aldehyde group the aldehyde functional group is always at the end or the terminus of the molecule. All right, so let's take a look here now at another example of something that contains an additional functional group or something else in the molecule. So here we have a compound. So let's take a close look at it. So first of all, you have to recognize what family it belongs to. So your C double bond OH, right? This tells you that it's an aldehyde. All right, and how many carbons do we have? Well, if this is an aldehyde, this has to be carbon 1, which means that's 2, this is 3, this is 4, and that's 5. So it's a 5-carbon aldehyde. Prefix for 5 is pent. So we start with the corresponding alkane, which would be pentane. We drop the E, replace it with Al, pentanal, and now we can see if we put a box around our longest chain, we see there's a methyl on carbon 2, so we're going to say 2-methyl pentanal. We don't need the 1 to say that the aldehyde is on carbon 1 because it's understood that it's going to be on carbon 1, because the aldehyde is always going to be at the end or the terminus of the molecule. All right, and that's different than what we're going to see with our ketones. Oops. All right, so your ketones is, when it comes to the naming system, the systematic way, the IUPAC way, is we're going to take the alkane name, drop the E, and replace with O-N-E, which is pronounced own, right? Not one. Right? So the ketones are going to have that O-N-E ending, the own ending. All right, so the simplest ketone that you can have, remember the ketones have the carbonyl surrounded by 2 carbons on either side. So the simplest ketone, or the smallest ketone, is going to have a C double bond O between 2 carbons on either side, right? Which will be 2 methyl groups. So here we have 1, 2, 3 carbons. So that would be propane. Would be the corresponding alkane. We drop the E, whoops, and replace it with O and E. So that the systematic name for that would be propanone, right? Which has a common name associated with it that is more commonly known as acetone, which is sometimes used as nail polish remover. The other way that we can name our ketones, so this is a common name, and also a common name would simply be to name the groups, the alkyl groups attached to the carbonyl, right? So we see here that there are 2 methyls, so we can also name this as dimethyl, and then we just have the word ketone at the end. So dimethyl ketone would be another name for propanone, right? Propanone would be the preferred way to name that, because that's the systematic way to name your ketones. If we take a look at maybe something slightly bigger, right? So if you had something like this, all right, and we had to name that, right? So first of all, you have to recognize what family it belongs to. There is your carbonyl between 2 carbons on either side, so that would make it a ketone. Right, let's see how many carbons we have in our longest chain. We have 1, 2, 3, 4, 5, 6 going from left to right, or 1, 2, 3, 4, 5, 6 going from right to left. Right, so the prefix for 6 would be hex. The corresponding alkane would be hexane. So we drop the ending E and we replace it with O-N-E, hexanone. And now when we get to these bigger and bigger carbon chains, we have to now specifically say where that carbonyl is located, right? And we want to number the chain to give the lowest number possible to that carbon. In this case, we want a number from right to left. Okay, and we can see that the carbonyl is on carbon 2. So we say that's 2-hexanone. Versus if we had something like this, 1, 2, 3, 4, 5, 6, and we had a double bond over here, right? Again, our longest chain would be 6 carbons. This would also be hexanone, right? But now that the carbonyl is on carbon 3, so we would say 3-hexanone. So for larger ketones, the location of the carbonyl must be specified in the name. Right? We have to say where that double bond, the C double bond O, is located. Notice we didn't need to say it in propanone because that carbonyl can only be in one position, right? It has to be in the central carbon. It couldn't be on the ends, otherwise it won't be a ketone. It would be an aldehyde. All right, let's take a look here at another example. Let's look at this one down here. Guess we're going to name this according to the IUPAC, or the systematic naming system. So we're going to identify this, right? There's our C double bond O surrounded by 2 carbons. That would make it a ketone. All right, our longest continuous carbon chain would be, that contains the carbonyl, would be 1, 2, 3, 4, 5. All right, so that would mean then that it's a pentanone. The carbonyl is on carbon 2, so it's 2-pentanone. And then, right, what you can also see here is that in addition to the carbonyl, we also have a methyl on carbon 4. So this would be 4-methyl 2-pentanone. All right, and that's systematically how you want to approach the naming of the ketones. In terms of the physical properties, we're going to see a similar trend as we saw with the alcohols, and that is small aldehydes and ketones, so on the order of 4 or fewer carbons, tend to be very soluble in water. You start making the aldehydes and ketones larger, the solubility in water tends to decrease. All right, and that's the same trend same general trend for the alcohols that we saw previously. Okay, so small aldehydes and ketones tend to be water soluble. Right, because they do contain that very polar carbonyl, as the number of carbons and correspondingly H's increases, the molecule becomes more nonpolar. Excuse me. And thus less soluble in water. Right? Remember, water is polar, and polar things will dissolve well in polar solvents. Okay, and I mentioned a couple of these aldehydes and ketones before, a couple of things that you may have seen or used. So acetone, which is the common name for propanone, right? So we have a 3-carbon ketone, and the skeletal structure would look like this. All right, that's, as you probably know, is used in nail polish remover, cleaning fluids, paints, etc. Formaldehyde, the simplest aldehyde there is, used in the preservation of biological specimens. All right, it's the simplest aldehyde, a 1-carbon aldehyde. That looks like that. A couple other ones that you may have used or come across that you may not necessarily have thought about. Benzaldehyde, which simply has an aldehyde connected to a benzene ring. Right, that's the common name for that substance. That's the flavoring agent that you find in almond. Vanillin, we actually saw this in the previous section, has the aldehyde group attached to phenol. And then cinnamaldehyde, so vanillin, by the way, found in vanilla. And then cinnamaldehyde, found in cinnamon, right, has the aldehyde functional group here at the end. All right, so these are very common things. They're found in lots of places, and they're responsible for typically the smell or the odor or the fragrance of these common substances. All right, so let's quickly take a look at these here to kind of recap. We're going to classify each of these as an aldehyde or a ketone. All right, so for A, there's our carbonyl. It's between 2 carbons, so that would make it a ketone. In B, there's our carbonyl. It's attached to at least one other hydrogen. That would make it an aldehyde. In C, there's our carbonyl. It's attached to one other hydrogen at least. That would make it an aldehyde. And in D, there's our C double bond O. There's our carbonyl. It's attached to 2 other carbons on either side. That would make it a ketone. It's a cyclic ketone. Specifically, right, the way that we would name this, right, we start with the alkane name. So a 6-carbon ring alkane would be cyclohexane. And then we drop the ending E, we replace it with ONE. Right, so that would be cyclohexanone, would be the systematic name for that cyclic ketone.